This lecture deals with the topic Maxwell's equation from fundamental laws. We know that there are several laws in electrostatics and magnetostatics. First, we are dealing with electrostatics. There Gauss's law, then different laws are there. Similarly, for magnetic field, magnetostatics also different laws are there. So we have studied about Gauss's law, Faraday's law, then Ampere's circuital law, etc. So first of all, we are dealing with static field. From Gauss's law, we can say that the total flux psi is equal to the total charge enclosed by the surface. Okay, so in mathematical form, we can write that psi is equal to Q enclosed. That is, psi can be written as the closed integral delta psi, if delta psi is the incremental flux, and that is equal to closed integral d dot ds. Also, we know that the charge Q is equal to the volume integral of rho v dv, where rho v is the charge density. Therefore, if we are considering this as equation number 1 and this as equation number 2, I can write closed integral d dot ds is equal to volume integral rho v dv. This is actually the integral form of Maxwell's equation. And by divergence theorem, I can write the surface integral del dot dv is equal to volume integral rho v dv. That means I can write del dot d is equal to rho v. This is actually the differential form. That means here this particular equation is from the divergence theorem. We know integral d dot ds, surface integral d dot ds is equal to volume integral del dot d dv. So that is origin. So now I have the Maxwell's equation in integral form as well as in differential form. That is from Gauss's law. Now in from the Gauss's law of magnetostatics, that means in magnetic field, if you are considering magnetic flux density, that is B is equal to d psi by ds. That means rate of change of flux through a unit area ds. Now here also psi is same, it is representing the flux, and s is the area. Now if b is equal to d psi by ds, then psi will be purely integral of b dot ds. But for an isolated magnetic charge, we know that isolated electric charge doesn't exist. If there is no charge, there is no motion. Therefore, isolated magnetic charge also doesn't exist. That means the total flux through a closed surface in a magnetic field is 0. That means what? Total flux through a closed surface is same as surface integral b dot ds, that is equal to 0. This is the integral form of equation from the Gauss's law of magnetostatics. Here also we can apply divergence theorem. Surface integral b dot ds is equal to volume integral del dot b dv. That means if surface integral b dot ds is 0, volume integral del dot b is also equal to 0. That means what? Del dot b is equal to 0, and this is actually the differential form. Okay. Now we are moving towards the third law, that is from the conservative nature of electrostatic field. When a charge is moved from A to B, the potential difference between the 2 points is denoted as VAB. That means we know that if you have 2 points, the point A and point B, that we have to do some amount of work for moving charge from point A to point B. Okay, so if you are moving from A to B, the potential difference is denoted as V of AB, and if you are moving from B to A, then the potential difference can be denoted as minus of VBA. Why? Because the second potential will be negative of the first potential. So we can write that VAB plus VBA is equal to 0. Okay, that means the surface integral, the closed integral, line integral, E dot dl is equal to 0 from this particular thing. Okay, and we can say that this is the integral form of the Maxwell's equation. Then according to Stokes' theorem, we can write the integral E dot dl is equal to surface integral del cross E ds. That means line integral E dot dl is equal to surface integral del cross E ds. If line integral E dot dl is equal to 0, then the right hand side also will be equal to 0. That means that del cross E is equal to 0. This is actually the differential form of third law. Okay, now we are moving towards Ampere's law. So from Ampere's law, I can write that the current enclosed is equal to line integral H dot dl. From Stokes' theorem, I can write line integral H dot dl is equal to surface integral del cross H ds. Also, we know one more thing, the current I is equal to integral J dot ds, where J is the current density. Now, if I is equal to integral J dot ds, let this be equation number 2, and it's the same current is equal to line integral H dot dl, let this be equation 1. By comparing 1 and 2, I can write the line integral H dot dl is equal to surface integral J dot ds. That means, if you are applying Stokes' theorem here on the LHS, line integral H dot dl is equal to integral, that means surface integral del cross H ds, and that will be same as surface integral J dot ds. If both the surface integrals are equal, then the terms inside the integral should be same. That means del cross H is equal to J. That is a differential form of the fourth law. Okay, so we have studied about the first law, second law, third law, and fourth law. First law from Gauss's law, and you have the integral form and differential form. Second law from Gauss's law again, but Gauss's law of magnetostatics. Here also you have the integral form and differential form. Third law from the conservative nature of electrostatic field. Here also we are having the integral form and differential form. And fourth law from the Ampere's circuital law, and here also we are having the integral form and differential form. So that's all about the static field. Now if we are moving towards the time varying field, what is happening is we couldn't say that for the first law we have proved like del dot D is equal to rho V, that is the differential form, and surface integral D dot ds is equal to volume integral rho V dV, that is the integral form. So in the time varying field we can consider the same thing. Q is equal to volume integral rho V dV, where rho V is the charge density, and from the definition we know that Q is equal to surface integral D dot ds. Therefore I can write surface integral D dot ds is equal to volume integral rho V dV, and therefore del dot D is equal to rho V. And secondly, integral B dot ds is equal to 0, that also we have proved. That means del dot B is equal to 0. Third one, Faraday's law states that the EMF induced in any closed circuit is equal to the rate of change of magnetic flux linkage in the circuit. That means if the magnetic flux that is linked to the circuit is changing, the rate of change of that will be equal to the EMF induced in that particular circuit. Okay, that means if the flux is changing, it will be converted to EMF. Okay, that is the meaning. So if IND is the induced EMF, then if psi is the magnetic flux, then we can write that according to Ampere's law, Faraday's law, V induced is equal to minus d psi by dt. And we know that psi is equal to surface integral B dot ds. Okay, therefore, if you are substituting for psi, I can write V induced is equal to minus d by dt of surface integral B dot ds. Or if I am taking the order of integration, I am changing the order of integration and differentiation, I can write minus surface integral dou B by dou t ds. This is equal to. And therefore I can write V induced is equal to line integral E dot dl. This is actually the definition, by general definition. So if you are comparing this particular equation, let this be 2 and this be 1. Comparing these two, I can write line integral E dot dl is equal to minus of surface integral dou B by dou t ds. This is actually the integral form of the third law. Now applying Stokes' theorem to this particular equation, I can write line integral E dot dl is equal to surface integral del cross E ds, and that is same as the RHS, that is minus dou B by dou t ds. Therefore I can write del cross E is equal to minus dou B by dou t. That is the differential form of the fourth law. Okay, and that of the last thing, that means if you are considering the fourth law, here you know that the fourth law is surface integral line integral h dot dl is equal to surface integral j dot ds, and that is the integral form, and del cross h is equal to j, that is a differential form. But we have studied earlier that if you have the current component and if you have the differential displacement current component, then line integral h dot dl is not surface integral j dot ds simply. It is having one more term, that would be in line integral h dot dl then turns to surface integral j plus jd ds, where jd is the displacement current density. Okay, so if that is happening, then I can write del cross h is equal to j plus dou d by dou t. That means for the time varying field, we have one more component with the RHS, that is dou d by dou t. So this is actually the differential and integral form of Maxwell's fourth law corresponding to time varying field. Okay, so if we are considering time varying field, there is no change for the first two laws, but in the second law, third law, we are having one change, and the fourth law, we are having one more term. That's all about the review of Maxwell's equation. Thank you.